So the thing I found, here's what I learned about YouTube, is sometimes, in particular, everything crashes the video, and you have to just reload.
Right.
Control
Okay.
Shift R. And sometimes you have to remove the cache, because it's like got too big a cache.
Oh, no. Okay.
Put anything else in it. So.
Interesting. Weren't you finding that as well, that you had to reload?
Yeah, but just once or twice.
We're live?
We're live.
All right, we're live. Great. So this is the 7th lecture. We're going to talk about sheaf cohomology. More or less, finally, we'll get some invariants for sheaves, and these will allow us to start understanding when you've got various kinds of defects or gaps in your data structures that we've been building. So now at this point, we've got sheaves built on topological spaces. We've got all the linear algebraic and homological algebraic tools at our disposal. And we've got the topology and the data put together. So now we can go to the very top of the diagram and combine them and start getting out reasonable topological summaries of your data that's stored in Sheaf. It's not so much topological, but it is sheaf theoretic invariants for the data stored in those sheaves. OK, so really what we want to do is we want to understand what do the global features of fused data look like, how do we compute them, how do we assemble them, and really understand how to find sheaf invariants. Now, the truth of the matter is what we want to do is we want to build them in much the same way we've been building homology for topological spaces. So how did we do that? We took our abstract simplicial complex or our topological space in that kind of format, and we wrote down a chain complex in which the chain spaces were based on the simplices, and the boundary maps were based on how the attachments worked. We did essentially the same sort of thing, where the chain spaces are going to be the stalks of the sheaf put together in an appropriate fashion, and the boundary maps will come from the restriction maps. So that's the idea. OK, so let's talk about this from the level of global sections, because that's the right place to start. And this is a very basic idea, is that if I want to have a global section of a sheaf, what has to happen? Well, I have to have data that agree. It says that if I have data on this vertex and data on this vertex, and they both map through a restriction map to the edge, that data agree. So graphically, here is the stalk of a sheaf S over a vertex V1. Here's the stalk over a sheaf S over vertex 2. Here's the stalk over the edge. And what I'm going to do is I'm going to map through the restriction maps. Now, to keep the discussion reasonably general, I'm going to use this notation here. Script S is for the sheaf, and then this is read A attached to B. This is a lower dimensional face. This is a higher dimensional face. So this is the restriction map that connects a cell A to B, or a simplex A to B, B being the higher dimensional one, A being the lower dimensional one. So in particular, this is then the restriction map from V1 to edge E, and this is the restriction map from V2 to edge E. Now, initially, we thought of these things as linear maps, and that works great when the stalks are all vector spaces, i.e. these are morphisms in the category of vector spaces. But these could, in fact, be, now we know, these could be other kinds of data spaces as well. Now, it really turns out, though, that you want the vector space structure in order to compute cohomology. And here's why. See, if I've got a global section, it means that I've specified data at these 3 data spaces, picked out an element of here, another element of here, and another element of here, so that when I map the element here over V1 through this restriction map, I get the element that's already here on the edge. And similarly, when I take the element out of this vertex, map it through this map, it ends up over here. Write that down as an equation. Map through the restriction maps from the vertex 1 to the edge. There's the data. I'll say S is a function that's assigning data from each vertex or each edge, from each simplex, to the data spaces. So this, you can think of it as a function on the simplices. So if I put in a simplex, it gives you out the data element that you're interested in. So here we go. That map from that data through this restriction map has to be equal to the map acting on the data coming from the other side. OK, so this equation, if satisfied, gives me a global section here. OK, now if I'm in a vector space, or at the very least an abelian group, what I can do is I can just subtract this from both sides. If I subtract this from both sides, I can set it equal to 0, good old algebra. I could have done it the other way. I could subtract it from the other side as well. But I come up with, in either case, I'm finding this equation equal to 0. So I've just rewritten the equation. Nothing fancier than that, and it's predicated on the fact that I'm able to do this because I'm in linear algebra land. Now, if I take one of these two equations here and look at it, it's something equal to 0. Something equal to 0 is good because it means that I can turn it into a matrix equation, where it's a block matrix. This is a function, so it's a matrix unto itself. Here's another matrix unto itself, and it's acting on this block vector. The block vector has components taken right here. So all I've done is I've factored out these maps, thinking of them as matrices, and now I've got this linear algebraic constraint. So what I've done is I've reduced the question of finding a global section to finding the kernel of a matrix. Now, if you think about it from the standpoint of what we talked about in the previous lecture, we were finding homology elements by finding kernels modding by image. So this is like finding a kernel. Oh, so this indicates that there's probably a good way to generalize this into some kind of kernel mod image construction. At least that's the suggestion. And for instance, let me make this concrete on a sheaf example. So here's the Q sheaf from several lectures ago, where we're moving data through time through a 3-element shift register. There's the sheaf. Here's a section of that sheaf, sort of zoomed in on the middle. So I've got a particular element, and I know that that element is a section because these elements live in a section because if I map them through the appropriate matrices, I get the data on the other faces. Great. So let me take this and take it out and think about it from the standpoint of this linear algebra that I just mentioned. So I've got now 4 restriction maps, and I've color-coded them. I've got the blue restriction map in the upper left. If I write down the appropriate equation to compute the global sections as a kernel, that matrix ended up right here. I've got another matrix, this red one. This one ended up over here. I've got the purple one and the orange one. And what you should notice is that if you're looking at this particular edge, remember, vertices, the restriction maps go out of, edges they go into. Looking at this particular edge, well, that is taking data that has come from this vertex and this vertex. Now, what are those vertices doing? Well, those vertices are mapping into this edge via those restriction maps, and I want to check them for consistency. So if I take this particular data, this particular element of the stalk over this vertex here, 192, is right here. And then the one on the other side, the vertex on the other side, the stalk is element 119 is right here. So if I now take this vector and multiply it by this pair of matrices, you'll notice what I'm doing is I'm subtracting. There's the minus sign attached to this particular restriction map. So I'm going to ask the difference between the data brought from this side and the data brought from that side. If they agree, I get 0. And indeed, I get 0. Now, the same thing happens for this edge, but now with data coming from this vertex and that vertex, and here they are. And so what we've done is, in order to compute this set of global sections, verify that this is a global section, is to verify merely that this vector lives in the kernel of this matrix. OK, yeah?
Go back one slide. Going forward. Oh, there. The S's are the vectors. So
The S's are the S of V1. These are vectors.
S ranges over all the sections.
So this S here, so this S is a subvector, so to speak. It's like a sub-block vector. This is over a particular stalk. So let's track where this guy shows up here. That's one of these elements on their own. So this particular guy could be a vector. In the example we were just looking at, this is a 3-dimensional vector. If this is a 3-dimensional vector and this is a 3-dimensional vector, this is then their vertical stacking of them. So then this is a 6-dimensional vector. This then has to be a something by 6 vector, or matrix rather. Something by 6, because this is then something by 3 and the same something by 3.
But it's a single section you're looking at.
That's right, I'm looking at a single section. That's right, I'm looking at a single section and verifying that, in this particular case, that this is a section by showing that when I construct the matrix, this matrix out of the various restriction maps. Sort of block popped them in there. When I block constructed this matrix and I then block constructed the elements of the stalks that I'm interested in testing, that I get 0 with that matrix multiplication. Yeah?
So if it doesn't come out to 0, does it appropriately get assigned blame?
Yes, it does, actually. It does appropriately assign blame. Let's say I took this and turned this into a 3. If I turn this guy into a 3, what happens? Well, row into column, I'm going to get nothing. I'm going to get a 1, 0, 0 here, right? And because that's 1 times 1, 1, 0, 0. And this is going to give me a 1, wait, no, I've got 1, negative 1, 0. So that those 1 and negative 1 adds to 0, so that's fine here. The problem shows up where? Actually, I guess that was a bad example. This 3 is fine. That example is OK. If instead I change this 9 to, say, an 8 or something, then it will show up right. Because what will happen is I should be matching up this 9 through here with this 9 right here, which should be a 9 matching up. If this is an 8, then I'll get something non-zero here, which says, where's the problem? The problem is at this particular edge. The problem is at this particular edge, which is then highlighting this edge, and in particular will highlight which slot in this edge. So yes, it does assign blame. OK. Other questions?
In that column vector, the third 2 and the very last 1 are irrelevant because they're moving.
Yes, that's right. Yep, those are indeed irrelevant. You're right. Yep. He said, it made the observation that this third 2 is irrelevant to whether or not it's a section or not, because it simply is never tested. Because if you look at it, this is a full column of zeros. There's another full column of zeros right here. This one, so that corresponds to this 5. That 5 is never used either. So this could be anything it wants. It'll still be a section. That's right. Anything else?
More the queue, looking at the queue itself.
Right.
The 2 is what's happening outside your region.
That's right.
What's happening to the
Absolutely. So the 2 is way off here. That's right. So this 2, the reason why it's irrelevant is because as far as the queue is concerned, I could have loaded anything onto this side of the queue. And this side over here, I could have had anything happening on that side. Yep. Very cool. All right. So this matrix then, this matrix is rather useful for determining global sections. The way that I pasted it together by block assembling the thing suggests that I can do this more generally. And here we go. So what I should do is these involve vertices and edges. Well, vertices and edges are 0 and 1-dimensional things. And what I did is, let me back up here. What did I do here? I took vertices, data on vertices, and mapped it through here to go from data from vertices to data on edges. So I went up in dimension. Homology went from data on edges and went down to vertices, or data on 2 simplices and went down to edges. Here it looks like we're going up. So we should build the same kind of chain complex, but we will go in the opposite direction. We'll go up in dimension. So in particular, then CK, what should C upper K be? It should be data associated to each of the K simplices. So it should be all of the stalks over K simplices. Glom them together, stack those vector spaces together, take the direct sum of them, if you like. So stack them together by concatenating bases. And then K plus 1, that's going to be, again, the stalks over the K plus 1 simplices. Stack them all together. K plus 2, that's all the data over the K plus 2 simplices, the stalks over the K plus 2 simplices. Stack them together. Now, what about these boundary maps, or the analog of the boundary maps? These, typically, people call them co-boundary maps to remind you that they're going up in dimension. These co-boundary maps are going to be built by gluing together a bunch of restriction maps. We'll see that in a moment. But regardless, if I do that right, if I build these maps correctly, then that same proof that we had wrote down in the last lecture, proving that we had a chain complex, that same proof will go through. And that'll mean that I have a chain complex, so immediately it has, as a chain complex, it has a homology, defined kernel mod image, as you might expect. To remind ourselves that the dimension is going up rather than down, we call it a cohomology, and this is called the Sheaf cohomology. So this is where we're aiming, so let's now sort of delve into the details. And let's remind ourselves that there's some notational reminders so that we don't mix up the indices. Because mixing up the indices is almost as endemic to mathematicians as mixing up the signs. We mess up signs an awful lot. We also mess up indices. So there's some reminders. If you've got a chain space and it's with a k down below, that says that we're dealing with homology, and we will be going down in dimension. We then call the maps boundary maps. If you're dealing with cohomology, the k's are upstairs. That says we're going up in dimension. We have co-boundary maps. And so as a result, we have the difference between homology and cohomology. Now, we'll talk a little bit more about this in terms of how it impacts your... First of all, is there a cohomology theory that doesn't involve sheaves? And the answer is yes, kind of. And we'll see that in a little bit. But right now, let's focus on constructing then these co-boundary maps for the sheaf cohomology. Yeah?
Go back 2 slides. So on that equation at the bottom,
Yep.
the way we were defining the quotient, we were taking away bases.
That's right.
Which would bring the dimension down.
That's right.
How is this working where it's bringing the dimension up?
OK, so all right, so there are several different things that are dimensions. There's the dimension of the simplices that we're putting data on. And then there's the dimension of the stalks, which store the data. So the question is, how do these interact? In the case of homology, there's only one dimension. That's the dimension of the simplices. Now we've got dimension of simplices and the data sitting on top of the simplices. And they're actually pretty close to being uncorrelated. So this is dealing with, the k's here are not dealing with the dimension of the stalks. They're only dealing with the dimension of the simplices. And in particular, you'll notice that the indices here are a little different than they were before. That rather than being from this being k and this being k plus 1 in the case of homology, this is k minus 1. To say that I'm taking the kernel of this modulo the image of this, like we were before.
Now, before we were taking away some of the bases.
That's right.
And that's why the dimension went down. Are we here?
We're doing this algebraic operation is the same operation.
Okay.
It's the same operation, but the difficulty, or the difference rather, is mental difficulty, is that we're dealing with the dimension of stalks. This is all happening on the level of stalks.
Oh, okay.
So you're right. There is some definite subtlety here in that difference of dimensions. Other questions? OK. All right. So as I said before, what we want to do is we want to build these chain spaces out of the stalks, primarily because that global section example I just gave you, what were we do? We were taking that big long vector, that 9 long vector that had the 3 blocks in it. That was a concatenation of the stalk over vertex, stalk over vertex, stalk over vertex. So we took all of those vertex stalks and concatenated them together. So if I do that, that's called a direct sum, where I concatenate bases. It's a way to make new vector spaces by concatenating bases. So exactly the thing you want to do is you want to walk over all the k simplices and gather up all of their stalks. This will be at least as long, well, it would seem like this would be at least as long as many k simplices as I have, but there could be some k simplices that have 0-dimensional stalks. We've seen this in particular when we were looking at sampling, where we had some places that were 0, because we simply weren't getting any information there. OK, now, there is one little comment here that I'm making. If you're working with abstract simplicial complexes, that's the end of it. If you generalize beyond abstract simplicial complexes, work with CW complexes, you have to be a little bit more careful. This does define a reasonable chain space, but it's not as reasonable for most examples. Most examples, you want to ignore any of the k simplices that are missing faces. In the Pi sheaf code, for instance, there is the marker asking for whether or not a face has compact closure. That's essentially what we're asking for. Is we're asking for everyone that has all of its faces. Reason being, they might be somewhat underdetermined. OK, so these are called, each element of this space is called a k cochain. And it really specifies data from all stalks on all k simplices. So you walk over all k simplices, you grab data out of each and every one of them. That's what this thing is. OK. So how do how do you build the maps? Well, you build the maps exactly the same way that I kind of suggested, which is you grab the restriction maps and drop them in there. Where do you drop them in? Well, you drop them in blockwise. You drop them in blockwise in the corresponding blocks. So if I'm looking at row I, column J, that corresponds to a particular cell. Now, these are block rows. This corresponds to a particular cell J, cell I. That's a higher dimensional, k+1 dimensional cell. And the column J, that's an input to this matrix. So that's a k-dimensional cell that corresponds to that block. And then within that block, you stick the restriction map that goes from the lower dimensional cell to the higher dimensional cell. And as before in the case of homology on a space, we've got this index in there. The index, orientation index, is keeping track of the fact that I would like in the end to have a chain complex. I'd like, in fact, to have that composition of contiguous maps to end up 0, consecutive maps to end up to be 0. So you drop in that orientation as well here. And the reason for that orientation is just as before. If you remember what we did when we had the equation for the global section, we had the two restrictions, and I moved one of them over to the other side, and it ended up with a minus sign. That minus sign is this guy right here. So we're keeping track of the fact that data could be coming in from various locations, and we'd like to subtract it all out to measure the difference at higher dimensional phases. So this particular construction yields then the right co-boundary map that I then have a cochain complex, or a chain complex, which we'll call the cochain complex. OK. So what we've done then is we've assembled this cochain complex for a sheaf. So given a sheaf of vector spaces, you can build the chain spaces, cochain spaces, and you can then build the co-boundary maps, just as I showed on the previous slide. And that thing does, in fact, turn out to be, once you do a little bit of work, it's basically the same proof as before, with a little bit of tweaking, but basically the same proof as before, that says that the thing is a chain complex, and so it has a homology, which we'll call Sheaf Cohomology. And really, what is it doing? At level k, at dimension k, what it's doing is it's asking for all of the cochains that when I go from level k to k+1, so I go and check them on higher dimensional simplices. When I check them, they lie in the kernel. They're consistent. They are the sort of things that when I did that global section check, I picked it up, moved it over to the other side, and got 0. It says consistent. On the other hand, I'm ignoring the ones that were already present. So take all of the data that are consistent at simplices of this dimension, but ignore the ones that have come from data from lower dimensional simplices. That's what this is. This is merely asking for that kind of consistent data that was non-redundant. OK. So let's go back to what does this mean? So H lower 0 is the space of global sections. Why? Well, it's specifying data at every 0 cochain, for every 0 cochain. What's a 0 cochain? That's all the data specified on vertices. Remember, all of the maps, restriction maps, go out of the vertices. They go out of the vertices, and therefore determine all of the data everywhere else on your simplicial complex. And so the kernel, then, of that co-boundary map is checking for consistency. So it is literally all of the consistent data over all of the specified all over the vertices. So I've got a vertex here and a vertex here, a vertex there. Those where I check consistency, if they come out to be 0 when I check consistency, i.e. they are consistent, then that's an element of H over 0. Notice that I don't actually have to worry about the image because I don't have -1 dimensional simplices. OK. Now, H upper 1 is a little more subtle, and that's usually where the action is. H upper 1 is, in essence, the loops, in essence, detecting the loops. However, these are not just loops. These are data loops. These are situations where I have data feedback. Where I have data feedback, these are situations where I have some kind of loopy belief propagation, some kind of recipe for disaster in some sense, or some kind of resonance condition. So in particular, and that's a theorem, if you're looking at wave propagation on graphs, anytime you have a resonance mode where you have a wave that starts up, travels around the loop, comes back exactly in phase with what it started with. That turns out to be an element of H upper 1. Those are resonant states. And really, that's the right intuition to think about these things. So they end up often looking very much like non-collapsible loops, but now we've got the additional constraint that the data is somehow consistent. Now, it turns out that like homology, and because homology is a functor, that sheaf cohomology is a functor, which means that it takes sheaves, and if I have two sheaves with a sheaf morphism between them, then in fact I get a linear map between the sheaf cohomologies. This means that cohomology is an accurate, or at least it is a precise analogy for what's going on the level of sheaves. This is very valuable for understanding the structure of sheaves and understanding how they relate to them.
So, just before you continue, what would be the corresponding intuition about H2 in this case, for the data case?
So it's some kind of higher dimensional loopy belief propagation. I don't actually really know. I don't actually really know, and honestly, what's that? Data voids. Yeah, in some sense. I mean, truth be told, what typically happens, and part of the reason why this is difficult to say things generally about this, is because in order to interpret what H upper 1 is meaning, requires some amount of domain knowledge about what the sheaf is telling me. The fact that I can compute this is domain agnostic, but its interpretation depends very much on the domain. And that's very true for higher dimensional sheaf cohomology as well, which is, it may be present in the data, I can see it and locate those cohomology classes and even track down what has given rise to them, as in what particular assignments of data gave rise to them. But their interpretation is not as obvious.
Okay, so in fact, I have come across H2 in different contexts, but perhaps it's misleading. You know, that first of all, the differential forms one.
Oh, sure.
Secondly, in
Sure.
algebraic K theory.
Sure.
I mean, algebraic K theory is so weird. It's
Agreed.
structure of rings, but it's best in that case not to take those intuitions here. Because
That's right.
Different.
I think you're probably right in saying that one should be very careful about making any kind of inferences about that. And thus far, I've not really seen a lot of higher sheaf cohomology of higher than 1 being something that I can nail down and say, I know exactly what this means.
Could it be like in group cohomology, you have H1 is relations between generators, and in H2 you have relations between...
Yeah, so it is something involving multi-way interaction. It's something involving multi-way interactions, but it's not entirely clear to me what it is. Okay, right. So one thing that we should nail down is the relationship between cohomology and homology. You know, if I have a chain complex of just a space, so that's the top guy with the boundary maps, I could transpose everything inside and come up with something that goes the other way. If I transpose a map, it flips the domain and range. This gives me another space, and this is the cochain complex. With real linear algebra, this thing is just finding functions on simplices rather than simplices themselves. And this, you know, in many cases carries identical information. It's encoded a little differently, but it's more or less identical. There's something called the universal coefficient theorem that tells you about that. If you look at this and say, well, you know, what are these co-boundary maps doing? And these now are, I'm saying co-boundary map because they're going up in dimension. They're just the transpose of the boundary map in the case of spaces. They work kind of like discrete derivatives, which is something that is kind of interesting in the sense that they end up being useful in asking for differences between data along an edge rather than between an edge. And this is really the intuition that we use sort of in another way when we're building up the sheaf cohomology, because what we're doing really is we're asking for differences between data. So if I have data on a vertex and another datum on a vertex, and I'm comparing them on the edge, essentially what I'm doing is I'm taking the difference, doing some kind of discrete derivative. So this actually works on the level of spaces as well. So there is a cohomology theory for just spaces that doesn't involve sheaves. And it's, in some sense, what we're dealing with then is what it's saying is when we're dealing with sheaf cohomology, we're actually looking at functions from the abstract simplicial complex, starting from all the vertices, edges, faces, etc., to what? To a collection of possible outputs where the output space can change as you move around the space. This gives you a good idea of what a sheaf is. A sheaf really is, it's a space in which, or it is a thing in which I'm looking at functions on a space. But the domain can vary, or the range can vary as I move around the domain. Sometimes people call this local coefficients. So functions with local coefficients are in fact sheaves. And this is an explanation for what. Okay. So let me now give you a very detailed example of a sheaf cohomology computation, because I think it will be very helpful to see how that plays out. Okay, so in particular, let's take a look at this simplicial complex. And let's look at what the various data spaces are. Well, what we've got is we've got this loop structure. Let me transfer it over to the board. And in essence, what we have is we've got a news source. We've got a web source. We've got a camera. And we've got a Twitter feed. These are the data sources. They are the vertices there. Additionally, we've got edges connecting them. So this edge checks whether or not there are clouds. This edge checks to see whether or not there is rain. This edge checks to see what the humidity is. And this checks to see whether or not there is sun or not. Okay. Well, if you sit down and write down what the possibilities are for what the data spaces are, build the sheaf model out, well, over the news, there is some data that they're giving. In fact, the question is, what data are they giving you? I don't actually know what the news feed is, but this should be the raw data of the news feed in some sense. This is some ontology, potentially a large ontology. And so I'm going to categorify it. So I'm going to take that ontology, which I'm going to call O1. And I'm going to look at the vectorification of that, a categorification of that. So I've got a real vector space built up on top of this ontology. Over here, what do I have? I've got the web. Again, I don't exactly know what it is, but it's got some ontology associated with it. Again, the Twitter's got some other ontology associated with it. I'm calling this one O3. And what does the camera give me? Not an ontology. It gives me a picture. Say an n by m picture. Now, when I start saying those are the data sources, now I need to start actually doing the multi-int integration and start pairing them together. Most of these are binary. Are there clouds? Well, that would be a yes or a no. That would be a binary. So I should categorify that much the same way I did the logic circuits. So it is either yes or no. It's a real dimensional vector space. The first basis element is for yes. Second is for no. Similarly for sun, and similarly for clouds. Now, what about humidity? Humidity is a number. It's 70% humid right now. I don't know. Okay, so these are supposed to be the maps. Okay, so there are my restriction maps, and they are whatever they are. Okay, so let me now write down what the chain or the cochain complex for this sheaf is. This is now a multi-int sheaf that is describing, a multimodal sheaf describing this scenario, this data collection scenario. And realize I'm leaving this somewhat underspecified. And it turns out that it's okay, because I don't know what ontology this is. Could be big. I don't know what ontology this is. Also, it could be big. But I'm going to say that there is some map that translates that ontology to a yes-no answer. So it ingests the ontology that you're hearing, the words that are being used to describe the weather, and we're going to pull out whether or not it's raining or not. Similarly, I'm going to pull out the words from this website and turn them into a yes-no answer to whether or not it's raining. Okay, so here's what the cochain complex looks like. So I've got, first of all, the zero-dimensional faces. Where are they? They are right here. These are the zero-dimensional faces. And so what I'm going to do is I'm going to form the zero cochains by writing them all down. By direct summing, the whole works by just concatenating bases. So concatenate the basis on of O2, concatenate the basis on O3. There are my three ontologies, as well as the space of pictures. So that's this whole thing here This is C0. Now, I've got a co-boundary map, D0. And where does it map? Well, it's going to map to the cochain space for the things that I have not underlined in red. And let me make sure I get them in the right order here. And these are, in particular, they are whether or not there is sun. So I'll label these. That's A. Then whether or not there are clouds. That's B. Whether or not it is raining. And what the humidity is. Okay.
Should it be R2 plus R2 plus R2 plus R?
R2, oh,
Because only
yep,
one of those is,
yep.
you know,
You're right. Thank you. Keep me honest. Okay, and that's C1. And are there any two-dimensional faces here? No. No two-dimensional faces to speak of. Okay. So now what I can do is I can sit down and say in a block diagonal form, let's pull back to here, in a block diagonal form, fill out that matrix, this co-boundary matrix. Erase what I've got here and insert it right here. So D0 is, now, it's going to be a block diagonal matrix. Let me list what the blocks are. This is the sun question, the A. This is the clouds question, the B. This is the rain question, C, and this is the humidity question, D. So there they all are. And now, let me list across the top here. This is the news. This is the web. This is the Twitter. And then this is the camera. Okay, and so I end up with this block matrix. Okay, so this block matrix, I can fill in some of this right away. This is a 0, 0, 0, 0. Those are all zeros because they're simply not connected. That there is no connection between the news and question, there is no connection between the news and the clouds question. The news and the clouds connection are not connected. There's no connection between the news and the humidity question either. So these blocks are 0. Now, on the other hand, what do I have in here? Well, I have some block. It's 2 by something. I don't know what that something is. This is also 2 by something. This is 2 by something. This is 1 by something. This is 2 by something. And this is a 1 by something, a 2 by something, and a 2 by something. I don't know what they all are. But each block that I filled in then is some kind of map. I don't know exactly what those maps are, but I can start bounding the rank of this matrix, which will start telling you about the size of the 0th and first cohomology. Now, the 0th cohomology is pretty big. There are lots of possible consistent sections. In particular, what this is saying, there's lots of possible ways to describe the weather. We knew that. That's uninteresting. However, if you look at H1, what is the kernel of this map? Well, it's everything. What's the dimension of that kernel? It's 2 plus 2 plus 2 plus 1. That is 7. So the dimension of this thing is dimension of this guy, dimension of the kernel of D1. The dimension of the kernel of D1 is 7. But what is the dimension of the image? Because I need to take the kernel modulo the image. Well, if you look at it, this map here, most of this map is probably not going to capture everything. And because particularly, each one of these blocks are full rank blocks, probably, which is to say the news can answer either yes or no. It is either sunny or not. The news can also say it's raining or not. Those are both conceivable things that could be said. Similarly, the web could say that it is raining or not, and it could list possibly, in principle, any level of humidity. Okay, so that indicates that each one of these blocks is a full rank. Well, if you start then doing a little bit of algebraic manipulation, you find out that just the way that we've put this thing together, this resulting matrix is not a full rank. A little bit of row reduction will show you that. So this matrix is rank deficient. What does that mean? It means that the image of this matrix is not a full rank, which means that there is something in the image, or something in this portion of the matrix that was never actually touched. Which means, in the end, that H upper 1 is not actually trivial. Which means that what are those things? Those are, in fact, the potentially locally consistent states of data that really don't make a whole heck of a lot of sense. So this is, in fact, a way that you can detect that you've got an information gap. That you could, in fact, there are opportunities to improve our description of the weather. How? By asking for corroboration between various of these sources in ways that you haven't checked. So, for instance, asking for the news to not just tell me about whether or not it's sunny or whether or not it's raining, but also to have them talk about the humidity and whether or not they're going to talk about the clouds as well. Now, they might. I mean, this is a constructed example. But the point is that if I can fill in this gap right here, that will end up eliminating the H upper 1, which is saying that I'm giving a more complete picture. So you can do these kind of computations extensively on this sort of multi-integration problem. You can also do this on some other simple examples as well. So let me move ahead here. So we talked about the logic functions. Actually, before I go talk logic functions, the questions on this. Yeah.
It's kind of a stupid question, but when you say sun, it's either sunny or not.
Yeah.
Why isn't that a logic?
It is a logic.
It is a logic.
It is some of a logic.
Why is it R2?
Okay, because what I've done is remember, I've said in the previous lectures that we need to categorify this so I can talk about these functions being linear. There's no, that's right, it's a vector space over true and false. In essence, you can think of it as kind of like telling probability. It may or may not exactly play out that way, but it kind of has that feel.
What about question marks and dimensionalities of the blocks?
Right.
Are those addressed, or do you need to?
You don't need to address them.
The analysis you made.
Right.
All you're asking, you're not actually calculating the full cohomology.
No, I'm not actually calculating.
Determining whether or not it's non-trivial.
I'm reasoning about whether it's non-trivial. If you wish to actually calculate it, then you do need to know those.
So how is that resolved?
So that is resolved by actually looking at the particular analytics that you're running. The particular analytic that will take a look at this ontology and make a determination about whether or not this is a yes or no situation. So that's a particular function that's going to ingest the ontology that's being
So
used.
the question marks are a function of those unspecified.
Those unspecified
the
analytics.
one
That's right. Yep.
And what N and M are in the image.
That's right. Yeah.
So would introducing those additional
Mhm.
consistencies give you like a higher dimensional
They-
simplex?
so they might.
And therefore shrink the kernel
Yes.
of that, and therefore.
That's exactly what
Yeah,
you do.
okay.
That's exactly what would happen is by adding additional consistency checks with higher dimensional simplices, you end up reducing this kernel.
Got it.
Yep, precisely.
So of course, this is outside the scope of this tutorial, but in the application case, you wouldn't actually have all these bits of information
No.
at the same time.
That's true.
So there'll be a time element, and also you might want to think that some are more acceptable as correct than others.
Yes.
Believable.
Yes.
So has anybody looked at this, or is this sort of work that hasn't been done?
This has not been done.
Okay, all right.
This has not been done.
All right.
Okay.
So why isn't the image of this rank 7? It looks like the way you could write it if you had
Okay.
numbers and you put in C0, it does look like you could get this to be rank 7.
Right. So in particular, this is one of those circulant matrices that if you write down reasonable full rank blocks for these things and start doing the row reduction, it usually comes out that it's rank deficient. I'm not saying it always does, but in most reasonable cases where each of these blocks turn out to be full rank, that it turns out to be rank deficient.
Yeah. So you're saying in most reasonable cases,
Right.
but it's not a mathematical property.
It's not a mathematical problem. Yes, you're right. Yep. Okay. So we talked a little bit about logic circuits. If I translate this logic circuit into a sheaf, I can sheafify it and examine its cohomology. And this does not have a cohomology thus far. This particular logic circuit is, well, it's something in particular because this AND function is not actually linear. Because it just doesn't satisfy the appropriate linear algebra requirements on this side. If I add 0 plus 0, I don't get 1, generally speaking. So if we categorify the thing, turn it into an appropriate vector space, this is now a vector space over each of these elements. Sort of note that turns out that turns into a tensor product. That's OK. Doesn't really matter. It's a 4-dimensional vector space then. And we saw this a little bit earlier where we build this kind of construction. So this is then what I had called a switching sheaf. Vectorified everything about this. Here I've got that linear map representing the and these are the linear maps representing projections. OK. Good as far as it goes. If I build out, say, one that has 3 inputs, then I have more inputs. Now, the thing to realize here is that do all of the edges in this have all of their faces? Does this edge here have both of its vertices? No, it only has one vertex. So when we start talking about cohomology of this thing, we don't actually end up worrying about anything but this. OK, it's simple enough. How many sections then are there? They're determined entirely by this particular space. This particular space is all of the various possible input and output combinations that I have. Turns out there's quite a few of them. And the question is, if I build a logically equivalent circuit, do I see something like that same number of sections? So if I build a logically equivalent circuit, here's another circuit with a similar flow tree, where instead of having a single 3-input gate, I have two 2-input gates, and I thread one of the inputs together. This gives me a 3-input circuit, but it's broken out a little differently. The data flows sort of top to bottom in this. And the question is, well, what do I get? Well, if I go ahead and make use of this cohomology, it turns out I can actually find something out. I could discriminate between this circuit and the previous one because the cohomology is different. It was 8-dimensional before. Now it's 6-dimensional. What happened? It's different. It's an invariant. It's telling me something useful. What's different? Well, what's different is actually that some of the sections have gotten glued together. Here are all the sections on the input. Here are all the sections on the output. Notice there's some overlap there. And so what that's saying is that we're representing transitional states a little differently. A model of uncertainty. That's kind of interesting. This doesn't have any higher dimensional cohomology. But the fact of the matter is, if I have higher dimensional cohomology, it starts representing storage of data. I'll give you an example of that very quickly. Sort of highlight this, and you can sit down and compute this. The cohomology over this particular circuit has non-trivial first cohomology. Notice this does not have a directed loop in the sense that it's got one input, one output, and one internal non-directed loop going out from this initial input, splitting out and going reconvening. That particular non-directed loop, however, stores data. It's got a race condition in it. This particular circuit, if you turn it on, it generates a small glitch, or turn it off, and it generates a small glitch. It's a glitch-generating circuit, which basically means logically it's supposed to always be at the same state, but if you mess with it, it doesn't. So that's kind of neat. Here's another circuit. This is actually a famous circuit. It is a set reflet set flip-flop. Having come from the electrical engineering curriculum, this is what we use to torment first-year electrical engineering students. Because we say, what does this circuit do? They've never seen a feedback in a circuit before. They start messing out and truth tabling the thing. Here's a truth table of part of it. Problem is that the output is fed back into the input. So the state of the circuit depends on its previous state. It's storing information. And it's not obvious what it does. It actually has a set condition. So if you set this particular choice of inputs, A and B, it'll store some data for you. It'll store a 1. If you do the reset, it'll store a 0. If you leave some of the inputs alone, it'll just hold on to that data for you. And then there's another situation where you hold it and it's sort of in an uncertain state. And whichever of the two inputs you release first, either A or C, and it really depends very much on fractions of a second, like nanosecond stuff, it'll pick one of the states for you. That's very, very interesting. Turns out this circuit ends up with non-trivial first cohomology, which tells you that it's storing information. And in fact, the truth table comes embedded in the rest of the cohomology of the circuit, which is kind of cute. And in particular, the cohomology includes the same states that you found in the truth table with some additional transitional states, telling you what happens when you hold it in that funny, unstable state and then let it go. So this is an invariant that you can compute right out of the sheaf model. And so final bonus in the last few minutes. So what co-sheaves, we mentioned co-sheaves for a while ago. Don't they have something to do with this? They're the same kind of construction. Well, the globality of co-sheaf sections is kind of bad, because unlike sheaves, where global sections live in H0, global sections of co-sheaves don't live in a given dimension. They live in top dimensional simplices. They don't live in necessarily all the same dimension, because the top dimensional simplices might be different. They may not all be of the same dimension. However, what's interesting is numerical instabilities in models that are represented by co-sheaves, like various kinds of finite element models, are modeled by co-sheaves. Those can show up if you have certain non-trivial, now, homology classes. Dimension goes down. So to give you an example of what this sort of thing might look like, here's a antenna with two of my students testing it out, and here's a numerical simulation of it that I ran. And what you can do is you can model this thing as having a narrow feed channel that opens up into an open aperture. And here's the signal traveling down the narrow feed channel. It's two complex values, one for the wave traveling towards the aperture and one for the reflected wave back. And then there are a bunch of integral transforms describing the rest of the thing. So this is a co-sheaf model of it. It's sort of incomplete because I'm missing the boundary conditions. There are the boundary conditions. This is a co-sheaf model then of that numerical and analytic simulation. If I try to write down the co-sheaf homology in exactly the same way we've been doing it, grab all the dimension 0 stalks, grab all the dimension 1 stalks, all the dimension 2 stalks, put them together, build a boundary map now. That's exactly what you do. Turns out the global sections end up spread across dimension 1 and 2, which is kind of awkward. So even though co-sheaves are great for modeling models, top-down models, the homological study of them is somewhat stymied by this. And I actually don't know a heck of a lot beyond that, and numerical analysts tend to work in situations where the top dimension is uniform across the entire complex, so this problem doesn't arise. So I don't actually know what to say about that beyond that, except to ask the question to say, if anyone wants to play with this, I'd be very interested to see what happens. So next up, we'll talk about computing homology and cohomology in software. And then the next and final lecture will be dealing with some noisy data.